Can you hear me? Can you hear me? Can you hear anything? Anyone hear me? User anyone can hear me? Anyone can hear me? I will upload the slide. Oh, can you hear me? Hi, Jevon. Are you online?
Yes, I'm online. Can you hear me?
Yeah, yes, I can hear you now.
Okay.
Yeah, please. So I have shared my slide. Can you see slide?
Yes, I can see the slides.
Oh, okay.
Then can you give me the presenter privilege so I can?
Yeah. Yes. So maybe I will help you all the who can grant the Jevon for presentation. So Jevon need to take control. Who can help? So okay. So
Never mind. Yeah, I can. Yeah, I can say that. So I think we probably should start. My name is Jiewon Yao. I'm a TDX architect for the virtual firmware and attestation. Today, Ken and I will talk about the secure bootloader for confidential computing. Let's go to page 4. In the first part, I will discuss the measurement and the trust chain setup. And in the second part, Ken will share the thoughts on the attestation and disk encryption solution. Next page. We have two typical use cases for the confidential computing in the cloud usage. And the figure in the left-hand side shows the confidential VM use case, and the OVMF is the virtual firmware. It launches the grub bootloader and the guest kernel initrd. And then the OS application in the VM OS. And the figure in the right-hand side shows a confidential container use case. The life cycle of container is much shorter than the VM. As such, it requires a lightweight virtual firmware. Here we use TD-shim to replace the OVMF in the TDX use case. And TD-shim can boot the kernel directly, then launch the container. Next page. The attestation is one most important feature in the confidential computing. This figure shows the remote attestation flow. The TCB underneath is a root of trust for the measurement. The virtual firmware, like OVMF, together with the bootloader and OS, create the chain of trust, which means the previous layer component record the measurement of the next layer into the measurement register. And the CPU may provide multiple measurement registers to record the different components. And the CPU hardware will generate a report for that include all the measurement registers and mark the report for ensure the integrity. Then a special component like coating enclave or coating TD can verify the MAC for the TD report and sign the report and make it into a TD code. And the code will be presented to the remote attestation server to allow the verifier to check the measurement register value inside of the TD code. And the code itself, you can treat it as a signature to include the measurement for TCB, measurement for the virtual BIOS, here is the OVMF, and the measurement for the OS. Here the OS means the bootloader like shim, grub, or kernel or initRD. And it can also be extended to more runtime measurements like dynamic kernel module. This figure shows the detail of the TD report and the measurement data structure. And the yellow part is a TDX module in SIEM, and it is the TCB, and there's a dedicated MR SIEM in the TD report. The green part is the initial firmware code. Here it is a boot firmware volume inside of OVMF. It is measured by the TCB SIEM TDX module in the SIEM, and the TD report uses the MRTD to record its value. And the rest blue blue is the firmware configuration. The red is the next firmware loaded code. Here it's a bootloader, and the purple is the OS kernel. They are recorded RTMR, which stands for runtime measurement register. They are extended by the initial boot firmware volume. The UEFI standard body defines the confidential computing extension in UEFI 2.10 and ACPI 6.5. It includes a EFI CC measurement protocol and a CCER ACPI table. And the CCER ACPI table records the measurement sequence into an event log, and each event entry is a measurement action. As such, the verifier can reproduce the measurement register value by using the event log. And currently, EDK2 OVF and shim and grub, they already such support. Next page, please. And this figure shows the TCC measurement flow in the pre-boot environment. The OVMF produced the CC measurement protocol and the CCER ACPI table. The OS loader like grub or shim, they can consume the CC measurement protocol to record more measurement records, such as a kernel or initRD. And finally, the attestation component can retrieve the data in the measurement register and the event log in the CCR ACPI entry to perform the verification. Next page. And here is an example we showed that the dump of the CC event log table, and we create a tool to retrieve it and print the TD report and dump the event log table. The tool is open source, so you can try it on any Intel TDX platform. And in that repository, we also include a full event log for the direct boot use case and the grub to boot use case. Besides the OVMF in VM use case, the TD shim in container use case also support the measurement to build the chain of trust. The flow in the TD shim is similar to the flow in the TDVF. The only difference is that in the direct boot use case, the shim firmware will launch the kernel directly. As such, the kernel is measured into RTMR1. While in the VM use case, the kernel is launched by the OS loader. As such, the OS loader is in RTMR1, while the OS is in RTMR2. But the rest part they're all same. The shim also produced a CCL ACPR table, so the runtime component can get that information. Next page. With all this background introduction, our transfer control to Ken, and he will lead a discussion on disk encryption solution in the second.
Thank you, Javen. So Javen introduced the measurement and trust chain. Based on the measurement and the trust chain, we can do attestation within the confidential environment. There are two there are two attestation usage. One is lunchtime attestation. In lunchtime attestation, so it is in pre-boot OMF phase or the early OS boot initiality phase. So for lunchtime, attestation can be used to get a key to decrypt the VM image view and view the full disk encryption tools in lunchtime. For OS runtime usage, the attestation agent can get the key from the remote key management server and then do maybe AI model decryption workload. So here we only discuss the lunchtime because it will impact the system boot in the guest. When we think about the disk decryption in the lunchtime, the attestation agent need to get the code. The code generated by the code generation service on the host or the bare metal, and after get the code, then the attestation agent will send the code to the remote key management servers. So we need to use the TLS to protect the data in the transfer, and we need a network stack. After get the key from the remote key management server, we can use the key to do the full disk decryption. So the argument here is how we establish the TLS stack, translation layer security, transport layer security stack, and how we establish the network stack to communicate with the remote management server. For example, if we implement a pre-boot disk decryptions, it means the attestation agent is running in pre-boot OMF phase, and the attestation agent in the OMF will call TDVM call to get the code. The TDVM call will pass the request to the host QGS service, and the QGS service will return the code back to the VM with the guest. And the OMF in the TD guest need to send the code to the remote server, right? So the OMF include the RESTful API HTTPS protocol and the TLS stack. But due to the security consideration, in the computer environment, the OMF will not include or enable the network stack. So we will pass the TLS request to the host TCP stack with the VM core or vSocket. Then send the request to the remote management servers. And the remote management server, key management server, disk key management server will return the key. Then the TDVF, the OMF will save the key to the ACPI table, storage volume key table. It's defined in the DHCS spec or ACPI 6.5. After got a key, the decrypt agent in the OMF or the grab in the pre-boot environment can do the can decrypt the disk because grab already supports the LUKS. But also you can let the initRD to do the decryption later in early OS boot time. So for pre-boot disk decryption, you can see there are a lot of benefit. So from talent perspective, because everything is get the key, get the quota, get the code, get the key is done by OMF. So there's no any impact to talent image. So it simplifies the talent effort to create the VM image. And it is flexible because you can support the grab to decrypt the disk, and you can support the decrypt agent to decrypt the disk, or you can leverage initRD to do disk decryption. But the cons, because the whole flow, attestation flow is done by OMF, so it needs a lot of change in different components, such as VM core, vSocket, host stack, and OMF. So this is the pre-boot disk decryption. And then we can design and implement the early boot decryption. Early boot decryption means the TDS agent is a Linux application running within the initRD. The initRD will invoke the TD code kernel driver, and the kernel driver will pass the code request to the host to generate the code. This is very similar with the OS runtime attestation because the TD agent in initRD is just a Linux application. After get the code, so the TD agent in initRD will establish the full TCP stack along with the TLS stack, and the TD agent in initRD will send the stack, send the request to the remote server, disk server, then get the key, then do the disk decryptions. So for the pros for these solutions, for early boot disk decryption solution is that the attestation process is running in user space like a normal runtime attestations. And because it does not require any change in the OMF, so in the VBIOS, so it can support different BIOS and bootloader such as OMF, such as GDShim for container use case. For cons that it may need modify the customer VM image. If you put the customized initRD in the VM get image, you need to modify it. But you can also pass the VM, the initRD image with the initRD command, launch command with QEMU. So this is two disk decryption solutions. One is the pre-boot disk decryption, and another is early boot disk decryption. So finally, we built the TDS MVP stack and open source as the GitHub. So in current phase, the TDS MVP stack includes a full component for the VM orchestrator use case. It means it can support libvirt to launch a QEMU, libvirt as the orchestrator's QEMU as a VM, and create the normal TD-VM for VM use case. Includes the attestation agent, bootloader, and the TD-get kernel. But in future, we plan to support kubelet use case. On the kubelet, you can launch the TD-VM with Kata will confidential container, kata-based confidential container, or you can create a TDVM and manage by KubeVirt. KubeVirt is a plugin to help manage the VM on the Kubernetes. But for the confidential on the Kubernetes use case, it requires TDCM and the Cloud Hypervisor also, beyond the QEMU and OMF. So the Kubernetes orchestrator use case is still working in progress. Okay, that's all our slides. So, any question or comments or suggestion? Sorry, I cannot hear anything. Can someone type in? Evan, can you hear anything?
No, I cannot hear anything.
Thank you for the talk.
Yes, I can hear you, David.
Yes, thank you for your talk. It's good that we could see the differences of both of the boot stacks, both the early and the pre-boot mechanisms.
Pre-boot, yeah. So what is your question? So so the question is that my question is signed key as you deploy the sign case as you deploy QEMU. So back to I'm not sure what you mean. So for sign key as you deployed in QEMUs, the do you mean the key part, the here, right? So QEMU, yeah. So Jiewen, do you want a response?
Actually, I'm not clear about the question. Is signing key means code signing key or something else? So
No, I cannot hear audience. I can only hear the David voice. I cannot hear others. Cannot.
Yeah, I cannot hear anything.
So if you talk about the code sign key, so the request the code.
No, the code signing key is not deployed to QEMU. It is generated by the coding enclave. It has no relationship with QEMU. I believe. So we must maintain the confidentiality of any signing key, so it won't be included in the QEMU.
Yeah, the code generation service is running on the host. So the request. Yeah, on the host. Yeah, so the TDVF or the OMF. So if you want to get the code, you need to pass the request. You need to pass the request to the host, and the service running on the host will help to generate the code. And sign the code. So I still cannot hear anything.
I don't know if I see this question from Dimitri and Michael. I think the bit that's not clear from your diagram is how the quoting is secure. Now I know that you have some enclaves to do that and TD calls and things, which I kind of vaguely understand. But I think if somebody's not seen this, they don't understand what keeps where the quote generation lives.
Kevin, do you?
Yeah. So coding enclave is a special is a confidential computing environment. So the enclave itself is signed. So it guarantees the confidentiality of the enclave content. So inside of this coding enclave, the enclave will verify the TD report to ensure the TD report has a valid MAC. That means it is really generated by a valid TDX machine. Then it will sign this TD report into a TD code. The key is the key to sign the TD code is generated at the coding enclave launch time. So then it use a X59 certificate chain, means the platform certificate key will be used to sign the code signing key, and the platform certificate key is signed by an Intel root key, which means if you get a code, you can verify the code signature by using the code public certificate. Then you can verify the code public certificate by using the platform certificate key. And you can verify the platform certificate key with the Intel root key. And that is how we create the certificate chain for the TD code. And we publish some library which can be used to finish this code retrieve and verification.
In addition to the Jevon, so before the code, so the report is got in the VM guest, and the report will be protected by some MAC key for integrity, and the TT report will send to the host, the code QGS on the host, and the QGS actually is running within another computational environment such as SGS or TDS. So yeah, so the QGS will verify the TD report from the guest as a local transition, then generate the code send it back to the VM guest. Yeah, any clear? Any more question?
So like here?
Yes.
Or where's the input? Okay.
So they can hear you on the remote, but not on the local. This is. Yes. Well,
So I would have to shout then, yeah?
Have you got this mic muted? Just repeat your question to that microphone.
I don't have a question. I'm trying to report. I'm trying to answer.
Okay.
Just more explanation for QGS. So here in this diagram, you can see the QGS is running SGS on the host, and so when the platform registration, you need to follow SGS platform registration to run the PCK tools to register platform.
Hello, everyone. I'm uploading my presentation right now. Is everyone hearing me all right? Okay, perfect. Thank you. Oh, I could hear some. Yeah, I could hear some sound. Yeah, is it working now? The on-site home? Okay, perfect. Sometimes.
Vincent, can you hear me?
Yes, I could hear you. The noise is not great. There's lots of noise, but I could somewhat hear you.
Nicole, can you hear that?
I'm sorry, I think it's pretty bad. Is anyone else hearing the on-site home? Because, yeah, I think I... Okay, perfect. So, thank you for having me at Linux Plumbers. That's a great, place for me to be right now. And I'm sorry in advance because it's the second presentation of the day, and I'm talking about System D. So, sorry about that. So, what I'm going to talk about is some work I've been doing in System D, which I called Secure Boot Automatic Enrollment. So in a first section, I'll try to explain where I come from, what is the goal of that, why do I even want that in the first place. Then I'll go over what I did exactly, and then I'll have a bunch of questions about that feature and if there's any feedback on this kind of feature. So first, my bio. I'm a former security researcher at the French Cybersecurity Agency. In France, I've been a sysadmin for quite a few years in different organizations. Well, I've seen a lot of places deploying systems, physical and virtual, and so that's where I come from. Pretty soon I'll be searching for a job, so if you have any job opportunity, let me know. So, my main goal is that throughout the different organizations that I've seen, UEFI and Secure Boot is still black magic for most users. When I'm talking about users here, I'm not just talking about end users, but I'm also talking about organizations. Lots of organizations don't know what to do with Secure Boot. Actually, I've been in plenty of them where the main thing you would do with Secure Boot would be to find a way to deactivate it as a first step. Kind of like what you would do with SE Linux if you ask a lot of people. it's too much of a worry. Let's just deactivate it. Now, I don't want to say that Linux with Secure Boot is not good, because it's actually really great with the shim project. There's been a lot of work on that project. Nowadays, you can just install Linux on a Secure Boot enabled computer really easily, and it just works. That's really nice. Now, using your own keys entirely is still not super convenient, and it often requires you using the UEFI UI, which might be of a varying degree of refinement, let's say. So basically, can we make it easier to use Secure Boot with your own keys without messing with weird UEFI firmware? So the solution I came with was automatic enrollment. Basically, Secure Boot keys on variables would be baked in your system. For example, if you have a deployment image that you deploy everywhere, you would bake in your keys in the system, and then they would be enrolled at the first boot. So you would have your keys in the image again, you deploy your image, and at first boot, it locks up the physical device. Now, with confidential computing, very conveniently, we just had a presentation about confidential computing. Well, with confidential computing, even in the cloud, you might start to have to want to be able to use Secure Boot. Actually, a part of why I developed this feature was because I was messing around with Google shielded VMs in the cloud, and I kind of wanted to test out Secure Boot, but yeah, it wasn't that great of an experience. So then I'm going to go really fast over that, because I'm assuming all of you are familiar with UEFI and Secure Boot. So Secure Boot, you know, it's a part of the UEFI spec. It was first in UEFI 2.3 in 2010. And then there's the Audit Mode feature from UEFI that was deployed in UEFI 2.5 in 2015. So that's going to be important, because I'll come back to that later. And basically, Secure Boot obviously allows the firmware to run on assigned binaries. So, Secure Boot keys. I want to go over that a little bit, because it's a nice refresher to know which keys are involved in Secure Boot. If you want the ultimate detail about all of the different keys, you can go check this blog post by, well, conveniently James Bottomley, which is somewhere in there. On his article lays out everything you need to know about Secure Boot keys. So basically, we've got 4 big kind of variables that are controlling Secure Boot in the UEFI firmware. You've got the PK, so the platform key. It's a single key, and its goal is only to update the next key, the key encryption keys. So the KEK is actually a list of keys that updates the DB or the DBX and can also sign binaries. Then you've got 2 variables that control which keys are essentially what is whitelisted and what is blacklisted, DB and DBX. So here, basically, the smallest setup you can have would be PK, KEK, and DB. DBX is essentially used for revocation of, for example, firmwares that have been compromised but were signed by a key in the KEK, for example, but it's not strictly necessary. And then there is MUX. if some of you have been messing with Secure Boot a lot, you know about MOCs, machine owner keys. So what about them? So MOCs are not in the UEFI spec. It took me an embarrassingly long amount of time to figure that out. I was getting confused with where are the machine owner keys defined in the UEFI spec. They're not. Like I was talking about with shim, basically shim uses MOCs as UEFI variable in order to allow you to add more keys without messing with the UEFI firmware itself on the normal hierarchy of keys. So this is an entirely different thing that I won't be talking about. Besides, I would rather not use shim as an intermediary before my bootloader. So my contribution, you've got the pull request over there on GitHub. Yes, sorry, systemd uses GitHub. On systemd as a bootloader. So if someone didn't know that, systemd took over your bootloader. It's actually it didn't start in systemd. It was formerly Gummy Boot. It's kind of minimalistic and it's UEFI only, which fits my bill because I want to develop this secure boot thing, which is going to be available only on UEFI anyway. So it has been merged and it should be available in v252. So it should be soon available on some distros. So what I developed already is that by telling systemd about a set of variable, so a set of pk, kek, and db, you can have systemd boot automatically unroll secure boot without user intervention at the next boot if you so wish. So it's not something that is forced. You can choose exactly how it happens. Basically, you drop your set of variables onto your ESP, so your system partition. And then you can choose to have them automatically enroll the next boot, or you can choose to have systemd boot prompt you whether you want to install these keys as your secure boot keys. So before any of that can happen, obviously the secure boot needs to be in setup mode. That's the main thing you need to do before being able to automatically enroll your variables. So basically, you drop your keys, you put your secure boot in setup mode. For now, you put a special configuration item in your bootloader configuration. So you put secure boot enrollment to force, and then your keys are going to be automatically enrolled next time you boot. And so you will transition from setup mode to, secure boot, full secure boot. So here, a very quick slide because really nothing very interesting happens. It's just about generating your own keys. So basically you generate a PK, you generate only one kek, and you generate 1 dB. You sign the PK with your PK because it's self-signed. You sign the kek with the PK, and then you sign the dB with the kek. Then you sign your kernel. You should probably not forget to do that because otherwise, yeah, bad things are going to happen. You also need to sign everything you need to boot, obviously. And that gets me to my next slide because you are probably already seeing a really big problem with this automatic process that enables secure boot. And yes, you are right. So, tinkering with secure boot can lock you out of your system. If you enable secure boot, but not everything that you needed to boot was signed properly, then you won't be able to boot anymore. Now, usually you just need to clear the UEFI NVRAM and you'll be fine. Now, it might be more complicated if you have some laptops. So in my initial pull request, Alexander and Morton brought up the case of some users with laptops that had option ROMs for their GPU. In this case, the option ROM is not going to get signed. It is not going to be loaded, and therefore the GPU is not going to work, which is going to be a pretty bad problem for laptop because, well, you won't have anything on your screen showing up, and even the external ports might be connected to the GPU, which means you won't even be able to connect a screen to see what's going on. So it's going to be fairly hard to get out of that situation. I suspect that there might be option ROMs for that are necessary for other stuff, like enterprise storage system and stuff like that. And so you should be very careful what you do that with, pretty obviously. So that's why we made it kind of difficult to mess up with all the options. But that's also why we're working on a potential solution, which would be involving UEFI audit mode on the TPM log. So the audit mode is something I talked about earlier. It was in the UEFI spec of 2015. And basically, it allows you to boot your system, and instead of denying boot when you reach some kind of verification failure, you can log it instead of denying it straight away. So that would be a way to make sure there are no bits that are not signed in the boot process, and only lock up secure boot if we see that there wasn't any failures. So before we get to the part where I have several questions for you, and I'm going to ask you to talk, to voice your opinions and questions, I want to thank first Nicola and Mikael, former colleagues of me, which have been tremendous inspiration for that. And I also want to thank Jan Johnson and Leonard Pertang for, they've been reviewing my PR and they've been great at it. And Systemd so far has been a wonderful community for a first contributor like me to work in. So thank you very much to them. During this entire process, I also did a lot of testing on the kernel EFI stub, was, well, kind of amazing. It's magic, to be honest. So I want to thank everyone who's been involved in the EFI stub kernel feature because, yeah, it's great. Thank you. So now it's going to be your time to talk. So I'm taking any feedback, comments, questions. I'm considering adding support for DBX, so the revocation list. Basically, For now, if you want to use multiple CACs, for example, you might want to use a third-party key in addition to your key, for example, Microsoft, it would probably be wise to also load the DBX, so yeah, that you don't allow bootloaders that have been known to be bad already. Then, like I mentioned, I want to eventually have a safer mode with audit mode on the TPM log. One of the hold up on that front is that I didn't find much resources that could tell me where I could find a UEFI firmware with audit mode. Like I haven't, none of my computers have it, and it seems to be pretty hard to find, which computer has this feature. More than that, I think EDK2 doesn't have audit mode support just yet. So yeah. So I think I'm done here. So I can take any questions if there are any. So you said you don't want to use shim to reduce number of bootloaders, but if we want to use shim, would it be possible to enroll your own mark and still have the firmware components like GPU, ROMs to be still functional? Yes. So the way shim works is that it essentially adds a stage to the verification. So yes, you could be able to do that. However, the thing is that you wouldn't be able to remove the keys that are already in the UEFI firmware. So basically, your shim will probably be signed by Microsoft, and so therefore it's valid. But you would still have third-party PK and third-party CAC, which is the problem I was trying to avoid. So, yeah. As long as you're keeping the original keys, there shouldn't be any problems with firmware components. And if you want to use that with, technically, I think if you want to use this method with the third-party keys in the cake, you could. The thing is that some of the keys, for example, Microsoft's key in the cake, has signed in the past stuff that's been vulnerable. So I wouldn't put a third-party cake without putting a DBX that has everything that's been revoked. So should we add support for bootctl? Yeah, eventually I think I want bootctl to be able to generate your secure boot keys. Now, like with any problem involving cryptography, the thing is just how involved do you want to be with managing keys? Because in the end, it ends up being the main problem. So you need to kind of keep, the thing is that you need to keep the keys around for signing more thing in the future, because whenever you're going to be updating your kernel, you might want to resign it. So that would be nice. So you end up managing keys, and my personal preference is to generally avoid managing keys. So when you say auto-enroll, I think you mean that you are installing new public keys used to sign your kernel into the UEFI. Yes, that's exactly what I mean. So by auto-enrolling, I mean that when your UEFI is in setup mode, the PK, KEK, DB, DBX are unprovisioned. There's nothing in them. And you fill them out. And once you fill out the PK, it transitions into enforcing mode. So enrollment is completed, you've loaded all of your public keys, and then it's only your keys now. I think the enrollment word, I think I got it from the spec. I'm not sure if I invented the term enrollment by myself. I think it comes from the spec. How many keys fit? Could I put a few extra in case I lose some? Well, so the PK is unique. So the PK, you better not lose it. Now, that said, it's only useful to sign the keks. So technically, there's only one, but at the same time, you only need it when you change keks. Now, the keks you can have, from what I can tell, any number you want. And technically, you could add more in there. I think the main problem would be with the DBX, actually. The thing is that the DBX is some kind of revocation list, that the NVRAM is actually available to UEFI is not that big, And I think eventually the DBX is going to be too big. I think the DBX would really be the problem first. And yes, like James Bottomley said, it's usually 64K. I mean, even if it was bigger, it's not really practical to do a lot of them. But yeah, so like James Bottomley is saying, there is a new revocation mechanism called SBAT, because essentially DBX is taking more space. DBX is a real problem on any large-scale deployments. So the KEK, the PK, and the DB live on the UEFI partition. They don't really live there. They just dob there. It's a UEFI secure variable, so it's signed. And then when the enrollment takes place, they're loaded into the NVRAM. Yes. Well, thank you everyone for having me, and good luck for the next presenter.
normal application processor. Your application processor and the T. So, and coming on to the peripherals, so there could be three categories of the peripherals. One could be the public peripherals that are available to the RE environment only, and there are trusted peripherals that are available to the T. And the third category is the special one, where you have shared trusted peripherals. So they have both modes of operation, like you have a crypto engine, which have one job ring available to the trusted environment and the others available to the RE environment. So that kind of peripheral can act as a shared trusted peripheral. And again, we have the concept of shared memory, where your host rich environment side shared memory is visible to the trusted environment applications. Now moving forward to one of the open source T implementation, that is Opti. So it is an open source implementation with the mainline Linux kernel driver. So the supported architectures are ARM and ARM64. So now people have started using adding support for RISC-V as well. So it's early stages, just booting Opti. And the main design goals for Opti is to provide the isolation that we talked about, and to have small footprints so that it's auditable and it's certifiable, that it's secure. And the third is portability. It's following the global platform T spec, so that your trusted applications, when you write for one T hardware-based environment, it's portable to the another T as well. And you don't need to have the main aspect that Opti provides is you don't need to have your hardware available with you. You can use your emulated environment using QEMU, and the support is available there. So we have the ARM Trust Zone solution that is emulated using QEMU, and you don't need to have actual hardware to play around with Opti. So I have put here a link. You could go through that. So just to give you a brief background about how the Opti looks like during boot. So this is a generic picture about how first starting off from the on-chip boot ROM, which loads and passes on control to the second stage bootloader. And the second stage bootloader is responsible for loading three components, that is a rich bootloader, the secure monitor firmware, and the trusted OS itself. And then the control flow you could see as picturized in the diagram. And finally, the rich bootloader would load the Linux kernel itself. This is how the runtime looks like and how the communication is established. Here you could see within the kernel, you could see the T subsystem and the Opti driver. And the communication mechanism, as I talked about, it's a secure monitor call in case of ARM Trust Zone, and it could be an IPC in case of AMD secure processor. So, and on the user space side, there is a generic T API, that is an ioctl interface that is exposed by the Linux kernel to the user space. And on top of that, we have the T client API, that's a library that is compliant with the global platform T spec. And on the secure world side, we have the T internal API. Again, that's a standardized API that is so that your trusted applications are portable. We have two kinds of trusted applications here. One that is running in the secure user space, and the second is running within the kernel on the secure side, that is known as sudo TA. So there may be some services that requires hardware access directly. So those kind of services could run in the secure kernel side as sudo trusted applications. Now, the main focus of this presentation, the Kernel T Subsystem. So it got introduced in the Linux kernel version 4.12. The T subsystem itself that provides registration and unregistration of T drivers. So there could be multiple implementations of the T. It could be an on-chip implementation and off-chip where you have a separate SOC, although you could consider Tpm as a T environment, but that's again fixed. But what T is, it provides you the programmability. You could program your secure end side, the trusted side. TPM is like a fixed piece of hardware. You could have a programmable SOC that you could say it's a trusted execution environment. And so what T provides you, you could have your own implementation for the T driver. And you have the shared memory interface between the normal world and the secure world. And in the T subsystem, during its when it got merged into the mainline, we have the Opti driver, which targets ARM and ARM64, and it has shared memory support via reserved memory. So basically, a chunk of memory that is reserved to communicate among the secure world and the normal world. Now we have AMD T driver as well in the upstream, and soon people are looking for Qualcomm T driver to be merged in upstream. So looking from the aspect of communication, so how the communication is established among the T and the RE. So first of all, a context is initialized. This is the API that is standardized, T initialize and finalize context. So among the RE and the T, the second bit that is done is establishing a session. A session is among the client application and the trusted application. So the API for that is T open and close session. So this is basically context is among the whole RE and the T, and the session is particular to the trusted application and the client application. Then we have within the session, we could invoke commands using session as a reference. And invoke command is basically you call a function of the trusted application to execute and provide you some results. Say for example, you want to have some access to the secure key, but it's not visible to the RE environment. You want to perform some operation using that secure key. That operation would be performed within the trusted application and you would get the results. So your secure key is not accessible to the RE environment and it's only accessible to the T. So that's one kind of operation. There could be other secure operation which you want to perform in the T side. Now coming on to how memory is shared among both. So this is the bit that was earlier implemented as reserved shared memory, where you have the buffers that are passed among the client and the trusted application. This is the reserved memory area, where if in case you have a pre-allocated client application memory, then it was like double copy. So it was first copied into the reserved memory and then copied back to the client application. But now with the evolution, we have this concept of registered shared memory or dynamic memory, where your allocated client application buffers or kernel buffers, anything that could be registered with your trusted OS. So you just split that into pages and you issue an command to the trusted OS to register those pages, so that we can work on zero copy concept, and the client application memory would be visible to the trusted application code. Now the second evolution that happened was to provide the in-kernel API. So there are various subsystems within the kernel, like RNG, crypto, or storage that want secure storage, that want the backend to be a T, so that like your secure keys, you don't want the kernel to access those, and you want operations to be performed by the T on kernel's behalf. So those kind of services can be provided by the in-kernel API, and it could directly communicate with the T is the kernel subsystem. So the exported APIs are listed here in the slide. So now we have the exported APIs, but how the drivers would be probed for a particular trusted application. So then we came up with this concept of T-bus, so that when you have the T is available in the T, then the driver should be automatically probed for those devices. So for that concept, we introduced this T bus in the kernel, and the concept is basically the driver registers a table of UUIDs that is corresponding to multiple TAs. So a driver could support multiple TAs, and it registers a table with the T bus. And whenever a trusted application becomes available on the T side, it would basically the driver for the T implementation would register that device on the bus, and if that UUID for that trusted application matches any of the driver UUID table, then the corresponding driver would be probed. So the APIs that are provided by the T-bus framework are match and UEvent. UEvent is basically to auto-load the T-bus drivers whenever the trusted applications become available. Now, since this device enumeration is very much specific to a particular T. Say, for example, we have Opti, because whether a device is available or not, or whether a trusted application is available or not, it depends on the corresponding implementation. And in case of Opti, we have a pseudo TA that is again a secure kernel service within the Opti, and it provides you the list of UUIDs that are present on the T side. So that could be enumerated, or that could be provided to the T bus as devices. And during probe for the Opti driver, it enumerates all the trusted applications which could act as a backend for the kernel drivers and registers on the T bus, and thereby the corresponding drivers are probed. So currently, Opti allows enumeration for pseudo and early TAs. So early TAs are just basically user space TAs which are bundled into the trusted OS image. That's why they are called early, because we need them at the boot time. Now coming on to the use cases. So first of all, the hardware Rng use case. So there could be cases where on a SOC you have a single entropy source, and both of the worlds want to access that. And because your secure world is the higher privileged one, and it wants the complete access of that, you don't want the real world to basically exploit that entropy source. So in that case, the access to the entropy source can be moderated via this T environment, via this hardware Rng pseudo TA. So the entropy source is only available to the T, and the kernel could use that entropy source via this hardware Rng pseudo TA. And in this case, we have this T hardware Rng driver within the kernel, and the pseudo TA is enumerated on the T bus, and then the service is accessible as normal hardware Rng TA. The second use case that is currently upstream, that is about trusted keys. So in case of trusted keys, so earlier it used to be only TPM based, and when I started looking at that use case, so it was basically sealing your keys with the TPM rooted super root key. So the SRK key is only accessible to the TPM, not outside. In similar manner, Opti has a concept of hardware unique key that is particular to the hardware only, and that's not accessible to the RE environment. And we can use that hardware unique key within the T to provide this use case of trusted keys, so that kernel is not aware about this hardware unique key. It just uses this trusted T driver to seal and unseal keys using that hardware unique key that is only accessible to the T. It is on the similar principle like SRK is available to the TPM only, and here hardware unique key is available to the T. And rest of the user space looks similar as for a TPM. The third use case is the firmware TPM. So firmware TPM with regards to Opti, it's basically a trusted application. And it works transparently with the TSS stack. So it is basically visible to the user space as /dev TPM0. And you could just perform the similar operation that you would do with the regular hardware TPM. So this is based on the Microsoft implementation for firmware TPM as a trusted application. And that is basically a software TPM implementation, and Microsoft implemented as a trusted application that is based on Opti. And there is already a Linux kernel FTPM driver upstream that is using that. I have provided the link here. You could refer that. The another interesting use case is this PKCS #11 token, where normally the PKCS #11 is like a crypto interface to the user space that is exposing services for various kind of tokens. That token could be a secure element, or it could be a hardware TPM device. Similarly, Opti, the trusted execution environment, could also present a token for the PKCS11, and the standard user space stack would work transparently with that. So in case of Opti, we provide this PKCS #11 trusted application that is part of the open source Opti project. And similarly, on the user space side, there is another library that is sitting on top of T client API that is called libckteak, that is providing you the PKCS interface towards the T. And your normal PKCS tool or client applications, they would work transparently as they would work with other tokens. So they would work with similarly with the PKCS #11 trusted application. Now, coming on to the future use case, this is something that I want to discuss here or brainstorm here about the kernel runtime measurements. A step towards tamper-proof runtime environment for trustworthy systems. So currently we have a static root of trust, like we do the secure boot or we do the launch time secure boot, but we don't have a solution for runtime kernel memory attestation or measuring the kernel memory at runtime. So there is a need for that, because it is possible to modify your kernel code or the text section at runtime as well. Say for example, you have done the secure boot during boot time, but it doesn't provide you the guarantee that the kernel memory or the text section would behave as done during the secure boot verification. So what I am proposing here is for the kernel runtime measurements. There have been some prior research on this topic, like the Linux kernel integrative measurement or kernel integrative measuring system based on trust zone. So it's basically measuring the runtime kernel memory. So I have just took this one of the research paper and how they are trying to propose this solution. One is, so what they are saying is you have the kernel and the modules, executable files, and you have the baseliner. So you have good values for your kernel and the modules. And when the kernel is at runtime, there is a measurer, or you measure the kernel memory at the runtime, and you compare those values with the ground truth. And then you decide whether any kind of unintended attack has been carried onto the kernel or not. So that's done by the LKIM appraiser. So this is an example which was done by the research. So how T could play an important role here? So T can act as a dynamic root of trust for measurement, such that the attestation key that is only accessible to the secure world. So the kernel, because kernel here is what we are trying to attest, or kernel memory we are trying to attest. So we don't trust the kernel itself, and the kernel memory can be registered dynamically, as we discussed earlier, for measurements with the trusted execution environment. And currently we already have something called as a remote attestation service that is provided by the OPTI, that is done for the trusted OS memory itself and the trusted applications memory as well. So we are measuring the runtime memories for the trusted applications as well, and we are signing that and providing a proof at runtime. And similarly, what I'm proposing here is for the kernel memory as well. So in this case, there is a possibility of replay attacks as well. So to counter that, we added a nonce, so that whenever a new signature is generated, that is a different one from the prior one. And now the question comes here, which kernel portions should we measure? The first one is the self. So the driver within the kernel that is providing an interface to the T, that should be attested firstly, so that we could trust the measurements that kernel driver is working correctly. Then there could be kernel text section, read-only data section, or any module-specific text section or read-only sections. And there are also critical data structures within the kernel. It could be security, subsystem related, or modules related. And there are also architecture-specific code and data sections. And there could be others that I may miss in this list. So for this purpose, this is the rough kind of initial draft which I had in mind, how the interface would look like. So the kernel T communication agent could just register a static list of kernel memory ranges. Basically, it would be start symbol and the end symbol for a particular section with the T. So the T has access to the kernel memory, all of it, whichever you want to measure. And then how you can trigger a measurement, you could just provide an updated nonce to this security FST file system and trigger a measurement at runtime. And then using this, you could fetch the measurements using a cat on this particular file. And lastly, this attestation public key. This is important. So it needs to be done only during device provisioning. So you can't trust at runtime the device provisioning key. So at the device provisioning time, you need to fetch that so that you could trust, and you could use that for the verification. So here, if you see at the measurements list, you would see start and end symbol, and then hash and the signature of hash plus nonce. So every time the signature would be new whenever you trigger a measurement again. But question comes here, this could be expensive at runtime, and your CPUs could be very constrained to do that at runtime. So what could be done to counter that is random measurements. You may want to reduce that measurement effort using random measurements. You could measure, say for example, some memory within the kernel, and next time you could measure another range. So in order to do that, what I thought is to provide the user space the flexibility to provide the list of sections that they want to measure. So there is a system.map file that could be useful here, which provides you the list of symbols, kernel symbols, if you want to measure that. So this is the second stage of the proposal, and we could modify the proposal with this measure range as well. So you could echo the particular symbol range which you want to measure, and based on that, you would fetch the corresponding measurement list. Now coming on to the threat model for this proposal, and first attack vector could be a man in the middle. So say for example, because we don't trust kernel, we say there is a malware sitting within the kernel that is trying to say this is the attestation which I have done. But how do we counter that? Is that attestation key is secured by the T, so that it's only accessible to the trusted execution environment and not outside. Secondly, the replay attack, as we talked about, the nonce. So
5 minutes left.
Yeah. Okay. Secondly, the nonce, which provides you the guarantee to avoid the replay attacks, so that you generate the signature every time the signature is new one. And lastly, since we don't trust the kernel T communication agent itself can be compromised, because this communication agent is providing the symbol range from which should be measured, and it's very much possible, or a very complicated attack could create duplicate memories. Say for example, you are not executing that particular kernel, but your communication agent has created a duplicate map for that, and do the measurement on that basis, and provide the remote entity a confidence that this is correct. To counter that, first of all, we would measure the kernel T communication agent as well, and secondly, there could be random kernel memory measurement, so that it's difficult to carry such an attack, so that there isn't a static list, and at runtime your remote entity could verify any particular memory region of the kernel. So that's all I had. And lastly, a few thoughts. Let's champion the open source T ecosystem. So there are already downstream T solution, and because of the security, or whether the companies don't want to upstream the T solution, but nowadays it's gaining traction to do open source T solution. So we should reduce the maintenance burden for the downstream T solution. And secondly, the future work that I think for this is proposing an RFC for the kernel runtime measurements. And if you have any other interesting T use cases, I'm happy to discuss that. Yeah.
Okay, any questions?
Any questions?
Hi, thanks for this presentation. So I don't think it's very useful to index to the symbol map. I think that ultimately you need to measure specific parts of the kernel, and if you're passing this off to a verifier who is going to produce some attestation results, that part really needs to know far more. It's not interesting to know from symbol X to symbol Y. It really needs to know what it was. In particular, you can also include the address, the physical address that you're measuring within your signature. And probably the nonce also has to come from the verifier over the network for that. So I think that you're better off just I think keep it simple, stupid is probably the right answer, and don't try to involve more pieces than you need to have.
Absolutely. Yeah. Keep it dynamic. That makes more sense.
So for what it's worth, there's an RFC in OpT that already does that, and it's based on exactly what you requested. So there's no symbols, there's nothing. It's a basically dumb API that says, here's the starting physical address, here's the length, go measure that, right? Okay. And the point is that you can't measure the entire kernel, obviously, because there's jump tables. The kernel basically changes the assembly that it runs at runtime once it boots. So initially we thought about doing this before we start executing the kernel, right? But that's basically undoable nowadays. So we need to figure out, portions of the kernel that we have to measure, and that's doable.
Yeah.
Right, Dr. Jens, we have an RFC on that.
Yeah. Definitely, I would be happy to look at that. Yeah.
So I actually have a question of threat model, because I'm not sure I fully understand it. So your threat model is that you want to measure the parts of a kernel to make sure that if there has been some modifications in the memory, you detect that. But you're using the component for measuring which resides in the kernel itself. So if I'm already able to get a write primitive into kernel memory,
So
how do you kind of protect from the, I mean, the kernel side is already under my control as an attacker. So measuring some parts of a kernel at that point is just kind of, I'm going to jump the other way.
okay, so you are talking about whether, so from the beginning, like the kernel communication agent is compromised, right?
So it can be compromised at any point of time because
Yeah.
it's a runtime memory. So if I go
Absolutely.
to write primitive into kernel memory, so I'm able to mount an attack. And from our security point of view, people, we consider from that point on write primitive in the kernel is under my control.
So this concept is based on top of secure boots. So from the starting point, so your kernel is verified during boot. So you could at least trust during boot that it's a verified kernel. And then at runtime, your kernel communication agent, as I explained earlier, that's an attack vector here. So the last one, if that's compromised, because we don't trust the kernel at all, because that's the entity which we are measuring. So how we can mitigate that is based. So the second mitigation is for the random measurements. Say for example, you have like man in the middle, like what you explained, like.
Who is doing the random measurements?
So it's the remote entity which is providing you the addresses.
Yeah, but who's going to provide, say, okay, the measurement for this part of the memory is, hash this. So who's going to do the actual measurement on the machine?
So it's here, this interface just provides you, the hash, right?
But that's under kernel control.
So kernel doesn't do any verification by itself. It's just providing you the hash.
Yeah,
the
but hash can be faked.
Yeah, that could change. And the remote entity has a ground truth.
Yeah, but I can provide you the ground truth if I'm an attacker. So
Yeah, that's why, because the signature is from TEE. So the T has the attestation key, and that can't be used by the kernel to create its own signature.
But when the T has to measure, it can't be the kernel itself.
Yeah, it's the T. Yeah, that's why I described it.
But one about agent.
Yeah, here. So the Linux kernel memory is registered dynamically with the T, and the T is the one that is measuring the kernel memory. So it's providing you the hash and a signature on top of that.
Okay, so the agent in the kernel is...
No, agent is just like providing the kernel symbols or the addresses to the T, which has to be measured.
Okay, so it doesn't do the measurement. Okay.
Yeah.
Okay, I think that we have to finish. We have a break. We will restart at 12:20. But before we wrap up, Michał want to mention one session which is related to our session.
So my colleagues from Google, Jonathan Zank and Ron Minnick, will give a birds of feathers presentation about Linux at Power Reset, status, challenges, and opportunities. Or they will talk a little bit about core boot Linux boot approach of putting Linux kernel inside the firmware and booting the Linux kernel as fast as possible on the platform. So feel free to attend this presentation. It will be held at the 5 p.m. at the meeting 6 room, I believe. Feel free to come. Thank you.
should be able to hear me as well when you're out there. So, okay.
I'll be a bit noisy, I'm afraid.
That is, you know, as long as we've got you.
Okay, this is me. Do you hear me?
I believe we want.
So I'm in the corridor now. You'll be hearing a lot of noise, I'm afraid. Actually, let's see if I can go into one of the quieter rooms. Okay, this should be slightly quieter. So somebody in the room say something. Well, if you're saying anything, I don't hear you.
how about the check, 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 check. Check, 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 check. Yeah, and that is the strange.
That's working.
That's working now?
Yep, I hear you now.
Are you? I literally just turned those on and turned them back off, or turned them off and turned them back. This is wow.
Well, it seems to be working.
Woo! That's scaring me. How about now?
Yeah.
Perfect.
You see the bar here, that bubble there is you.
I've changed nothing. Okay. Woo. Okay. I'm going to
The gain is still a bit high.
Yes, I'll turn that down. Okay, so that would be right here. Check, 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 check. So feel a little better. Okay. Oh, thank you. Yep, you are fine. Thank you. Yes, so this is where presenters will be. Check, 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 check. Hello, hello, hello.
Should we check just to see if we can do remote?
Yeah,
Why don't I
absolutely.
from the room?
Do it. Dude, that's
Doesn't matter at the moment.
no, I can turn that down from here. So let's try it. Wow. I just turned it off and turned it.
Turn on then.
Oh my goodness. I definitely don't want, we're going to have to probably turn this back on again. Okay. B.
Okay,
That
this
would
should be a
be him.
remote presenter.
Yep.
You hear me okay? I think you do.
Yep, we have you. Great. That's, I am I'm gonna super glue the screen. We're good. Woo, buddy. All right, one more photo. All right. Boy, oh boy, oh boy. Now you should hear everything in those headphones except for the mics in the room. You should hear everything else. Woo. Also, like, really and I got like new ones, and they. Oh, really? Well, this is like 12 or something. This is not answer. Yeah, so this is back to back. So to grab well, it might say, well, that's what I was well, exactly. Yeah, so
Yeah, thank you. I think that we can restart our session. Oh, I hope that. So we'll start our session, and the next presentation is. I forgot. A remote attestation of IoT devices using discrete TPM. Michał is setting up everything. I hope that the audio issue was solved. That this time we will have no such problems with our audio. So let's start. We cannot hear you. Dimitar? Could you use... Dimitar, can you hear us?
I can hear you. Yeah.
Perfect. Thanks.
Now it seems to be working.
Yep.
Awesome.
You can start.
I can start. Awesome. Thank you.
Yep.
And sorry for this. Okay, so I'll try to be quick so we have more time for questions. And unfortunately, the live demo I'll do will be slightly different from the one I had envisioned, but I couldn't find the router to connect the board. So let's start. I'm assuming here that there is knowledge in the audience about attestation and TPM in general. So I will just jump straight to the technical part. Svet would have been here with me, but he couldn't join us. So one quick clarification, we are actually from Bulgaria. It's a country in Eastern Europe. Our neighbors are Romania, Greece, and actually a bit above Romania is Ukraine. And yeah, just to give you an orientation where we are in the world. So why are we doing what we're doing? On one side, security in internet connected devices in general has not been adequate. Of course, it depends on what you want to protect, what is your threat model. Still, we see that end users and overall enterprise devices are not well protected. And this is true also for embedded systems. So while end users benefit from attestation and the technology of having regular evidence about the health of the system, and I'm of course talking about Microsoft Windows and so on, and now cloud users are benefiting from that as well, thanks to some efforts at Google and others, like Keyline, for example, for containers. This was not available for IoT and edge devices. So moving forward, why attestation is something that we need as an industry, or even as advanced users, if you will, because secure boot is definitely not enough. It gives us this one guarantee at the start of the system, and literally a second later, the moment you boot, you don't know what's the state of your system. And the danger is that whenever your system is changed, it continues to run. With IoT devices, this can be months on a battery, even somewhere very remote. Like I've designed one device for IoT tracking in the mountain, right? So stuff like that, unless you haven't a firmware update or the battery is changed, there's no reboot, no guarantee. This gets even scarier when we talk about edge devices that are constantly powered on, the routing data that have compute power to do things. So attestation helps us by providing continuous check. And the great thing I like about attestation that it's customizable. What we protect, what we measure, is up to us. So I'm just checking the clock. So again, I want to have more time for questions rather than having me just talking. There are at least 2 topics that I would love to discuss in this talk. So how do we do that? This is very high scope, big picture. We have our Enactrust Security Cloud, and on the other side, there is our Enactrust agent. Now, where this agent lives is a very interesting question. Of course, we want it to be in a memory isolated space. Is that necessarily Trust Zone M? Is that necessarily hardware provided memory isolation? Is it just an MPU, a memory protection unit? It's really up to the use case, to the customer, and to the system. We were surprised to find out that actually in industrial systems, companies lack adequate security to a degree where they want Enactrust regardless of the fact that they don't have Trust Zone. They just want to have attestation and regular evidence about the device health check. So this is just a big overview, and then what we use as a hardware root of trust. Okay, maybe it's a secure element, maybe it's a trusted platform module, or maybe we're using the built-in cryptography acceleration together with some OTP or just secure memory in Trust Zone. It's really up to the use case. In this particular talk, I'll focus, of course, on the TPM case and a discrete TPM, not a firmware TPM. And although this has been difficult for the past several quarters because of the shortage of chips, still we see a rising adoption of TPMs in industrial systems and embedded systems in general. And of course, having a discrete TPM has its pros, as I'm sure most of the audience knows. The physical tamper-proof side channel attacks and stuff like that are more difficult. So all this, I guess, it sounds obvious and even easy to people who have experience with TPM or attestation. But the fact is that attestation with a TPM for Cortex-M based devices did not exist before Enactrust. Of course, we have to mention, honorable mention, for the Azure Sphere that came out in 2017. At the time, I even just wrote in my blog post that actually Microsoft annihilated everyone by having a solution where everybody else was keeping it behind closed doors, right? Because I'm sure proprietary remote attestation solutions exist to perform these checks, to create an evidence inside a hardware security module connected to our main SoC or whatever. So the bad thing about Microsoft Azure, well, it's done in a way that corporations like to do it, in a very vendor-locked way. You can choose either MediaTek or the newest NXP, and that's it. However, the industry has spoken back to Microsoft saying, well, this is great, but we don't want to use just 2 chips, right? You cannot tell Samsung or some smart fridge manufacturer what chips to use because they're actually looking at features, at prices, and so on and so on. So Microsoft Azure Sphere, although great, it has 2 drawbacks. First, it's centralized. You need to use Microsoft Azure. That's it, period. Whereas with our solution, it's up to you. Do you want it on-premise? Do you want it with AWS? Do you want it with Microsoft IoT Central, Azure IoT Central? Up to you. Where Microsoft have been really trying to force the customers to say, hey, use our infrastructure and you're worries-free. And that's valid in some cases. So that's the first drawback, centralization. And the second one, it runs only on 2 chips. And recently, Qualcomm also announced they're releasing something with Microsoft Azure Sphere. But again, nothing to be seen yet, and 3 is not that much better than 2. So just going a step back, sorry, and I'm just rushing to it so we get to a discussion point. One thing more that is a drawback for all these systems is actually that the Azure Sphere is firmware solution typically that lives in a Cortex M4 that is a coprocessor to the main Cortex A, like the MediaTek, the NXP IMX8, they're all Cortex A plus Cortex M. So what I'm trying to hint here is that embedded systems like industrial sensors, smart metering for energy companies that are really vulnerable and in the field, those devices cannot be captured by Microsoft Azure Sphere. They cannot be protected by Microsoft Azure Sphere. And this is what we're trying to break. We even have a proof of concept for Cortex M0 that just has an MPU. And that's per customer request. So again, there are trade-offs, and we don't. We prefer to have trust zone in there. We prefer to have a physical TPM. Sometimes that's not possible. Sometimes you have to use a firmware TPM. Sometimes you even have to use just a secure element. What I'm trying to hint here is that we are trying to break the barrier and say, hey, it's easy to use it, but it didn't exist before, so take it with a grain of salt. We're just the first one trying to do this. And probably we didn't do everything right, but we definitely are raising the security threshold. So it's a bit more difficult for attackers, and it's a bit more obvious when your device doesn't send a fresh evidence or where the evidence doesn't match. At least you get awareness, right? We cut the time to response. So attestation available today. Here I've gathered what I'm aware of that you can try out. You can literally download it today from GitHub and try it out. So we target IoT and edge devices. I've talked about the different hardware root of truth that it's up to really to the use case. Where Keyline, another great example, open source project, target containers, has a dependency on Linux IMA. And by the way, Tori Summer, who is one of the maintainers, will be talking at our TPM Dev conference about the new things, the advanced stuff, and maybe how you can have evidences without the Linux IMA with their new Rust agent. So this is all great, but it targets containers, servers. It's used by IBM Research in their cloud right now. So IBM ACS, very old. At the same time, it's working. It's a reference. It's a working reference. It has dependence on the IBM stack that is dependent on Linux. Nokia 810 attestation engine from Ian Oliver. Also a reference, it works, you can use it. Also targets more high-end servers, Linux-based embedded devices. So what we're trying to do is either go in the other way. And now here I'm trying already. I would be happy to take some questions, although I'm not at the end of the talk. Let me know if there's something. I'll check the chat because here it gets really interesting. Some of the challenges that we faced, because I'm not claiming that we have all the answer. I'm just here to share our experience and what we did. So first challenge with attestation. Hey, is enrolling a TPM chip, a hardware security module, the same as enrolling the device? Not really, not in the physical world, right? At the same time, we have to make that assumption, again, depending on the use case. So often what we do is we enroll the TPM with its public EK key, the unique key that comes from manufacturing time. Then we create a certificate for the device. Maybe we create LDF ID and so on. But typically for attestation, you have to make that assumption. It's not always the case, but this is what we did in our case, that enrolling the TPM, because this is done typically either at manufacturing time of the IoT device or by personnel before the device is shipped in the field. So it's done by someone configuring the edge device, shipping it to a customer. So we know it is. We know what is the state. We know what is the good known state. So for us, enrolling the TPM is enrolling the device, and of course, a different setup is possible. But this is what we see to be the preference. So, in my opinion, it's interesting to explore the other possibilities, right? So then, once you have the system enrolled, the TPM enrolled, gets the question, okay, who can make attestation? Who can create evidences? Well, the TCG spec actually recommends the attestation key to have no authorization. No, like anyone could create an evidence. Why bother protect that? And this is a good approach because you would catch the evidence is different. The order of measuring files on the system or measuring file streams or whatever you want to protect, if it's different, you'd catch it because the PCR register containing the evidence, the hash digest, will be different. Also, in case the actual integrity is different, right? The file integrity is changed, you would catch that too. So actually, having a new authorization on the attestation key is, in my opinion, sound. But this is where it gets interesting. For example, Nico Williams in the next bullet point here on the well-known key for TPM attestation proposes that unless you have a clear set bit in the policy for what was it for one of the flags of the key, you cannot use it for attestation. Then Imran Desai in a talk about TPM2 policy gets even further by saying what PCR policies you can combine. That's really interesting. I really recommend Imran Desai, who is the maintainer of the TPM2 tools. He really debunked this complex topic. So policy over attestation key is something we even saw recently from Ernesto, a researcher at Infineon, who is using sealed keys for attestation. And this has its applications to have a policy over when the key can be used. In our experience, that's not really necessary. For one, the key lives in the TPM. Second, we use it only from our secure space where the agent runs. And then even if someone generates an evidence and send it, we would catch that it's different, the order or the integrity. And that's a simplification, but at the same time, you would catch if it's just one evidence that is false and so on. So these two interesting talks I'm recommending because Tromel Hudson, the author of SafeBoot, and Nick Williams came about to a interesting method of using a non-TPM key, what they call a well-known key, then to import and duplicate that key and use that to perform attestation. So actually the key comes from inside, wrapped in the activate credential, make credential challenge response mechanism. It's really interesting. And this is why I've put these topics here, because again, we've made choices, we made design choices. Some of them are customizables, you can change one way or another. Some we have set for now, but still I'm trying to share what we puzzled around. Hey, should we have a TPM2 policy over the attestation key? Should it be a well-known key that comes from the attestation server rather than generated on the spot, right? And again, the enrolling question is really a good one. So moving forward, design choices. One design choice from the start was to not use OptE. It is my personal opinion, just me, that OptE is bloated. It has too much things in it. Even the ARM Trust Zone recommendation is to put a minimum code base in, right, the secure world. OptE doesn't seem to follow that, and I know there's a lot of good effort there. I know that there has been great work done there. At the same time, it's firmware at this size. Even if you configure it, you customize it. This comes from the FAQ that the typical configuration is about 200 kilobytes. Let's say that's too much. Like it's too much for a device that is memory constrained, that is performance constrained. It's too much. So we've chosen a different approach. We've taken the TFM, which let's say a typical default configuration, it's about 60 kilobytes, 64, and we've modified it to have the NAV Trust agent. So we're not running as a trustlet or some kind of a trusted application. We rather modify that. And one of our benefits is that what we attest is customizable. We can attest the bootloader because we run in parallel. We're the first to run. We can attest device identity or configuration or anything that is of interest, user data and so on. So I'm rushing because I'm seeing that actually we have 15 minutes and I really want to take some questions in. So Tfm challenges. Well, our attestation evidence is tamper-proof, right? It's created in the TPM. It's signed. We will capture data integrity issues, man-in-the-middle attack with the nonce, with the fresh nonce. But still, who owns the network stack? Who is actually the one owning the network driver? And with TFM, you can have it either the trust zone controls it, or the normal world controls it, or it's shared. I myself was never able to get that to work. So you have to choose, okay, trust zone is sending a payload to normal world to send. Well, that's very easy to do the now service, right? You don't get fresh evidence. You say the device is not trusted. What do? That's a smart metering device on an energy plant. You send an alert every day that someone DDoSed your devices and you need to shut down the plant or check it manually, or like it doesn't seem to be a good strategy. But for some cases, like smart home devices, hey, it's not a big issue, right? Let's have trust zone there. Just generate the evidence in a secure manner. Send the payload to normal world. The normal world is responsible to sending it to the attestation server. So that's another question, another challenge, I think, when doing attestation in trust zone that I would love to discuss. Yeah, so what I'll show right now, because actually I couldn't find the router to connect the board, is I'll show you the quick start version that is available on GitHub. So we open the attestation server. Okay, I had the wrong link. That's interesting. That's here, h3s. Okay, it's without the www. So I'll just show you the quick start version. So we make the agent. Let me just maybe I zoom a bit more. Okay, so we have 3 commands here: enact on board, start to run as a Linux service. The quick start version for Linux is to lower the barrier for evaluating attestation. It's not the TFM version. For the TFM version, just drop an email to Svet, and he'll provide you access. So when we enter our dashboard, and I want to really type the link here rather than have it. Yeah, okay, I'm already logged in. So we have our dashboard, and let's say here we have TPM enrolled from a device. We have the TPM certificate, that it's a real certificate. And then we have also an integration with a key factor, which is a PKI as a service provider. We have generated a device ID certificate to use. And we also have some interesting feature about safety critical systems. We can actually attest the state of a GPIO of the TPM, but that, I guess, is for extra talk afterwards. So we have number of evidence, good status, all that. So let's onboard a new node here. And let me just prepare my screen a bit. So I'll take this command. And because I'm under Linux, not on the actual port, I need to do this. So I'm onboarding, I'm adding a new device to my system. And it says here that it's protecting the demo folder and it's protecting the password file of Linux. So now that I refresh, we'll see, okay, I have a new device. We have the TPM certificate. We have the PKI certificate generated for my device. Locally, you should be able to also see the same node ID here and here. So let's have our fresh evidence, because right now we don't have an evidence. So we generate an evidence, and now we have the good known state of the system. You have one evidence, it's good. So let me add an attacker as a user. Just let's say someone adds a user, and we catch this. Let me generate a new evidence. There we go. And of course, the state will be bad. And this is a great thing I like about attestation, because actually what you feed to compute the hash and then to the PCI register, it's up to you. It could be a file stream. It could be RAM. Like, it's up really to the application, to the Naxos agent in trust zone to decide what to read from the normal world and what to actually attest, what to verify. So before restoring the state, I want to go to the demo folder here quickly and say, hey, let's not listen to one specific address for SSH. Oh, I need permissions. Let's listen for all addresses, right? This is, again, silly, but it actually happens on routers. And let's prepare a new evidence again. and we'll see that we have now 3 in total. Our state is still bad. The device case lock, in this case, it's not accurate because I'm running the quick start version on the board. I could have shown you this. So now if I delete the user, right, delete attacker, okay, great. I generate the new evidence. Of course, our state will still be bad. Okay, that's surprising. I'm not actually protecting the demo folder. Huh. The surprises of live demos. What do you know? It seems I'm not protecting the demo folder. Check. I'm on master branch. Okay, well, that was surprising to me too. So that's the demo in a nutshell. I'll stop here to get your questions. Yeah, that was funny. So let me stop sharing my screen now. Any questions?
No? Yes? Yes, it works. Cool.
It works, yeah.
It's Michael. So that was interesting that when you enrolled a new device or that test device, so what protects your server from having thousands of devices enrolled by packers?
That's a good question. Well, this is just for simplicity. So this is the public-facing server that everyone can use to evaluate and try attestation. So we've tried to make it simple that all devices go under the user ID. So right now, you've seen my user ID, and you could actually add as many devices as you want up to a limit that we've set, and I think it's either 50 or 100 per like a beta user.
Any other questions? Mamy coś na czacie? No questions.
Okay.
You?
I see that maybe in the chat there was some discussion about the SPCs, those MediaTek and XPC with Microsoft Pluton. Well, it's a variant of Pluton. So the Pluton for embedded devices is still a firmware. It's different from the Pluton that goes into Intel CPUs and so on. The one in Qualcomm is expected to be actually a Pluton core, so silicon. Okay, so the deal that, and this is public information, so the deal that Microsoft made was with Intel, AMD, and Qualcomm that they will be integrating Pluton silicon in their CPUs. And this will be a fact that maybe in 10 years, when you buy an Intel or AMD system, it will not be having a TPM, it will be having a Pluton. And by the way, I'm still waiting on this Pluton public API. There is one guy very active in Twitter, CISO of Microsoft or something like that. I wrote to him like 5 times asking about the public API. Never got a response. Haven't seen it. I doubt anyone has, but yeah. So I prefer having a TPM rather than Pluton right now.
Dimitar, please read the question on the chat, if you can.
Okay, where does the measurement in your world start into the TPM? Is it from the initial boot block or trust zone code in the chip? Good question. Unfortunately, we don't have access to the trust zone ROM boot code, right? So NACTrust is the first to start. We are configuring the trust zone parameters, shared memory, peripherals access, and then the first thing we measure, let's say it's the U-boot bootloader before passing control to the normal world. And then what U-boot boots, it's up to U-boot. The good thing is that we can even continue further as we continue to live in parallel in trust zone, right? The agent continues to live. So we can attest different stages as well. I hope I answered the question.
Okay, any other questions for the audience?
You mean question for me?
One more question.
Awesome.
Hi, Ian. So I just wanted to add maybe that my opinion is that 90% of the problem with remote attestation is in the server and the stuff and the configuration that you've done. And so that's why I think it's really cool, even if you can't start at the very, very, very beginning, that it's still useful because, you know, generation 3, maybe you'll have enough volume that you can actually find the right NDAs. And that my experience is why people get screwed up with remote attestation, is because usually you can't do anything until you buy 100,000 parts from your vendor. And since you don't know if your product's successful, you aren't going to buy that many parts. And so you don't put remote attestation in your device because you can't afford to do it in the first day. And I think it's very useful to say, hey, well, maybe you can do it not quite perfect. Maybe good enough, perfect is the enemy of good enough here, and version 2 can be better.
Exactly. I thank you so much for this. Yeah, because the problem right now is it didn't exist. We had Microsoft Azure Sphere that's vendor locked, which is not bad. I'm not saying Azure Sphere actually did a lot of things right. The issue is that you're centralized, the servers at Microsoft, where in our case, you can run on an actual server, you know, let's talk about it. It's one of our use cases, how we started with the car manufacturer last year. They actually asked us, hey, we like this, but we want it on premise. Done, no problem. We're using AWS. Okay, great. Done, you know. This was our POC. Right? So what we're trying to achieve is give an attestation service for people creating embedded systems to use, evaluate, and try. And yeah, let's make it better.
Okay, I think that we should wrap up this session. Thank you for presentation and for joining.
Thank you for the opportunity. Thank you, really. Appreciate it.
Okay, thanks a lot.
And in the next 2 minutes, in the next 2 minutes, we'll have Daniel Smith talking about the Transit project and the status update of the upstream process into the Linux kernel.
Just a quick check of my mic before we start.
It works. Can you hear us?
Yep, I can hear you guys.
Perfect. I think that we can start, Daniel.
Okay, thanks. Let me go to... All right. Greetings, everybody. My name's Daniel Smith. I have Russ Phillipson also here virtually. We're going to do a status on Trench Boot, specifically discussing both the beginning as early launch capabilities, as well as the new relaunch capability that we're looking at. So just to review what we're going to go over, we'll do an update on the Trench Boot development, review the existing state. We'll go over the new SLRT and DL stub to help support the UEFI stub requirements. And then we'll step into the secure relaunch capability, give an overview of what we're building there, and then just kind of touch on some next things in a roadmap. So the existing secure launch series, as we wrote the first 5 iterations of this, most of the focus was on how to get the kernel started post dynamic launch. So for those that aren't familiar, when you do a dynamic launch, a hardware-based dynamic launch like you have on Intel and AMD, the CPU goes into a different state. How to interact with it is slightly different than what you're normally used to, in particular when it comes to AP management. So one of the things that we have to do very, very early on, as soon as we come in, is to get the world to look right from a CPU perspective. So a lot of the work was done in ensuring that's correct. And then the next thing was to actually capture as accurate of a record as possible of what the Linux environment looked like when it got started. So when you take all of that, so what that winds up resulting is basically 3 areas of changes that have happened. So there's the introduction of the SL stub, which understands how the ACM or the SKL from a is expected to jump into the kernel. So that way, as I state, it will then set up the world correctly for the from the CPU perspective. It'll set the weight block for the APs as it's bringing up the BSP and all that. Then there's the setup kernel, which we've introduced as an SL main function, which kind of is the core setup logic, kind of records all the measurements that it needs to be taken to record what the environment has. And then there's the kernel proper pieces, which is through the function slaunch, and it kind of provides the final setup and validation, while the SL module provides the runtime support, so access to the DRTM log, and on TXT platforms, access to some of the TXT registers and so forth. So what does that kind of look like? This is effectively what the flow looks like for the existing secure launch. So you have a boot manager and a bootloader, with your typical EFI environments that set up the Linux kernel, puts information into the boot protocol, and then calls the DRTM event to trigger the CPU to do the whole dynamic launch sequence. That winds up landing you in the SL stub, which will pull information from the protocol, and then passes along to the setup kernel and then to the kernel proper. So your typical flow after that point. So it's key here. One of the things to understand that there's been a lot of discussions over this is that there is information that is passed across this boundary. This is why we have the Linux boot protocol setting across the boundary. This is it. The way dynamic launch is designed to work is that the untrusted environment is responsible for setting up the world that will be jumped into. And then it's the responsibility, and there's a controlled sequence done as part of the dynamic launch to ensure that you accurately measure what gets started. So whatever gets set up by the unsecure world will be measured before it begins executing on the secure side. All right, so just to provide a little context, so anybody that's been working on this on dynamic launch for the almost 20 some years that the capability's been around, always winds up leading towards the architecture which it was designed. So you can see that the similarities are very similar between Microsoft and what we've done with secure launch, and that's not because of any copying, but that's just how the architecture drives you. There's a certain way it's supposed to be used. So as you can see, Microsoft does the same thing. They have this win loader that basically sets up the configuration information that's going to get passed across the DRTM event, and it's the responsibility of the TCP launch that was measured by the CPU to consume that information, measure it, and then you act upon it at that point. All right, so now we get to the wrinkle that we've been dealing with for the last few months, which is compatibility between the way Linux uses UEFI and most OSs use UEFI and how dynamic launch was intended to be used. So for EFI support in Linux, there is the EFI stub, which is a peer entry point to the SL stub for the Linux kernel. And one of the requirements is that the EFI, when you're launching in an EFI environment, the requirement is that you really should be going through the EFI stub for it to properly set up the kernel based off of the EFI environment. So therefore, it needs to have access to boot services. Well, this is where the wrinkle comes in, because dynamic launch can't be done until after boot services goes away, because EFI expects to have control over all APs, and once you tell the CPU to, if you don't have all those APs in the quiescent state, the dynamic launch will actually fault, and it could potentially lock the system. So all depend on what happens when you attempt to do the dynamic launch. So we have a situation where we need to be able to allow EFI stub to do what it needs to do, call EBS, and then for us to then be able to do the dynamic launch. So after a group call that we had with Matthew Garrett and so put together by Matthew Garrett and with several people, and we talked it over, there was a proposal to implement the concept of a hook function that the EFI stub could then use to call to trigger the dynamic launch after it was done. But the problem is that now causes us to have to go back to the drawing board, right? Because we had this flow of how we wanted to move everything, and now we have to introduce this whole new hook function that allows you to come into the kernel, come back out, and then go back into the kernel again. And it brings up several questions that we now have to answer, right? So as I was mentioning before, it's expected that the pre-launch world, the unsecure world, the untrusted world, is going to configure the environment and set it up and provide it. And there's bits of information that's expected to be put there for the dynamic launch to occur. So we now have to figure out a way, how do we persist this information between going into and out of the kernel and making all that information available? Where should it live? What all needs to be passed in it? What should it look like? And ultimately, while we're focused on Linux, we want Trench Boot, one of the goals for Trench Boot is to make all of our solutions agnostic, so that a way you can have this unified or common approach and implementation that occurs across any operating system kernel that wants to take advantage of dynamic launch. So after some internal meetings and a lot of thinking, we came up with two aspects. There's the DL stub and the secure launch resource table. And basically what this all revolves around is the DL stub is the answer to the hook function, and the secure launch resource table, the SLRT, is the answer for how do we contain all the information necessary to go between the launches, across the launch. So the DL stub, after some discussions about where that should live, we all decided that it really, from our implementation standpoint, it'll be a static binary that contains the minimal logic to get the system into a quiescent state and then trigger the logic, or trigger the launch, excuse me. That will ensure that such a little static binary can be reused across any platform and won't have any Linux specific information necessary for it. And all this code already exists it's effectively the pre-launch code that we've already had in Grub to trigger the launch. We can just now make it into just this standalone binary that at this point we'll probably package with Grub to put in place. The other piece of information, or the other part of this, is the SLRT, like I said. And it will hold all the relevant information, where the DL stub was put in place by the bootloader, any of the dynamic launch metadata, anything that the OS needs to store in there to convey what it did with the environment before we start the launch. And then all of this, both the SLRT and the DL stub, will get installed into memory by the bootloader, so that it will linked, and then it will be registered in a well-known GUID in the configuration table on EFI, so that a way it's easily locatable for any OS, including, in this case specifically, EFI stub can just look to see if the GUID is in the configuration table, and if it is, it knows that there should be a hook defined in there that it can then make the call once it's done. And then this same approach it makes it cross-platform for this approach, and cross-architecture and cross-OS. So what does that wind up looking like? Or I'm sorry, let me get to the details of SLRT before I get to the flow. Apologies. So the SLRT, what we went with was a tag length value style table design. so that way we can easily expand and enable and backwards and forwards compatibility. So in memory, it basically consists of a header followed by one or more entries, which are all the entries are TLV entries. And then obviously then we can easily implement some helper functions to search across them and then add entries to it. Represented here is basically for the minimal table would look like for a TXT launch, right? There is the header, the DL info, so that the kernel knows where to find the DL stub, and then there's the TXT info for the necessary information for TXT. So with that, this is how this winds up looking using that same diagram that we've been using thus far. So we have the boot manager. The boot manager can load up Linux and set up the and hand control the EFI stub. The EFI stub can make use of the boot services as it needs. It will find that there's an SLRT there, and therefore it will then call into the DL stub. The DL stub will make what little changes it needs to the SLRT, if any, and then it will trigger the launch. And then the rest of it is as we already have had in the past. So this change really only kind of focus. Well, I guess there is some more changes in the SL stub and everything else that we have to do based on some of the proposals for the SLRT. But for the most part, the flow kind of stays the same on the right-hand side. And we make adjustments on the left-hand side to deal with meeting the requirements of EFI stub. So with that covers everything that's going on with the early launch capability for secure launch. The next part is DRTM late launch. So with DRTM late launch, just to bring a common understanding, as far as dynamic launch is concerned, there are two types of dynamic launches: early launch and late launch. So early launch is what we've been focused on thus far, right? The coupling of a dynamic launch with the system boot. So this is that is where we've been at so far. Late launch is the next evolution of this, or the next phase of this work, which is the ability to do a dynamic launch at any time during a single power life cycle of a system. So you can, and it can be done any number of times. There's no limit to this. So that means that if there becomes questions about the state of the system, whether you want to go through an upgrade path through a dynamic launch without doing full hardware reboot and still be able to establish trust, this is what DRTM brings you. I gave a talk a couple of years ago about all these kinds of use cases you can do with late launch. Late launch is really the killer app for dynamic launch, because it allows us to, again, as I stated, it allows us to reestablish the DRTM measurements in the PCRs from a known good starting position, specifically the CPU. And then at that point, that new state can be attested to. And one of the other things is that, as I know, since it's going, you're not actually doing a power cycle, you can preserve state across the late launch. In particular, for a hypervisor could relaunch itself, but leave it and with its VMs paused, and then regain control over its VMs and continue on. So that brings some very powerful use cases, as I stated. So for now, as we're introducing this, we're going to call this secure relaunch, just to brand it a little bit. So how does this relaunch work? So the goal here was to introduce as little changes to Linux as possible. If we can, and what we've done in conjunction with the work that we did for EFI with the SLRT and these things, actually wound up making this easier for us to be able to accomplish this without having to do much to the Linux kernel or the kexec user space binaries. So the approach we're going right now is, as Grub already has all the support for initiating the dynamic launch event, what we're going to do is introduce a new platform to Grub called gexec. And what gexec is basically done is it allows you to, if you're familiar with Grub, you can basically do a make image with using something like uroot, which is already aware of dynamic launch, and build a bootable binary, a kexecable binary bootloader that will do a dynamic launch for you when it's been jumped into. So it winds up providing a separate entry point to capture which will basically capture all the past information or the previous information that's being passed across the kexec image that will be necessary for the relaunch. There's some modifications that will have to be done to the existing dynamic launch code for the relaunch. But overall, pretty much all the changes can be contained in what we're already doing for Grub. And then it can be used by others if people prefer to use some other solution as Grub. So like I said, there will be no changes to kexec. There'll be no changes to the Linux kernel to add this capability. So using that similar flow diagrams that we've been using to express this, so what will happen is you'll have a running Linux kernel, kexec will be fired off to set up the gexec image into memory. Gexec still does the DL stub, like I highlighted before, we're reusing this work. Except for in this case, it can just jump straight to it without having to worry about going through the EFI handler. Go into the DL stub. The DL stub will then, you populate the SLRT as it needs, do the event, and then we wind up on the same exact path as we did for the early launch on the other side. So what would this look like? So as I stated, you just need to build Grub with the new gexec platform. Once you've got it installed, all you need to do is just do a Grub make image specifically for the gexec platform, providing it what your Grub config will be, which you can see in the second block there, of being able to do a secure launch of the kernel without having to reboot the system. So that pretty much covers the relaunch capability. So where are we going next? Obviously, as we talked about, there's this new redesign that we did and that we're building on for the SLRT and the DL stub. So we're working to get all that codified into the patch series, so that way we can get a V6 of the secure launch kernel series out to the list for review. We'll be working on getting all our Grub patches at least posted to the Trench Boots branch tree for Grub, so that all the Grub changes will be public and usable, while we then eventually work on getting them upstream to Grub. Obviously, since the new series is going to introduce the SL stub or the DL stub and the SLRT, that means you need a bootloader capable of setting that up before calling EFI. So obviously there will be Grub changes that will need to be ready for that before we can, or that'll coincide, and therefore whichever one, they'll have to be released together. And then after we get all that work out the door, we'll be hopefully having the gexec work coming right behind it. Also on our roadmap, or on our radar that's coming fast, is finishing up the AMD support we already have some preliminary patches for, getting those into shape for submission to the LKML. And then we're also already starting to look forward to the doing ARM DRTM, since their spec is in beta right now, and there's work being done to enable, at least in TFA, some preliminary DRTM support, so we'll be able to prototype with that. So that's kind of where we're going with everything. Just a short little plug on behalf of Oracle. If this kind of stuff interests you and you really want to work on this, Oracle has Daniel Keeper's there in the room, so if you're interested, you can speak with him. I believe there's some flyers around out there as well. And so with that, any questions?
Any questions?
Hello. That's too loud. Okay. Hi, I'm Dimitri from Canonical Ubuntu. Can we have backwards of this to grub 202 and Linux 415, please?
Well,
grub 202 and Linux 415.
So I think you're putting the cart before the horse a little bit. I'd at least like to get it into the kernel before we start worrying about backports. But with that said, we have had, I mean, we've been working on it for a time. We have versions of the series that's against 415. But
are you there?
Can you not hear me anymore?
Maybe he's on mute.
Did you guys?
Yeah.
Can you hear me now?
We can hear you.
I don't think the room can hear me now.
I should just stop talking, right? Because I jinxed every single speaker.
No, I think my laughter did it.
It's your laughter was too loud,
Yeah,
and
everybody quit the hangout, right?
because they couldn't imagine porting it back to 4.x. Yeah. Oh, I don't think they're coming back.
I'm still here.
We switched to chat room.
We are in chat with him. Just a second. Now can you hear me?
Yeah. I don't know what to say. Let me.
You're very quiet.
There. How about that?
A bit better.
Okay. I cycled mute.
Right.
I don't know what I'm wondering if it dropped out when I stopped sharing or something.
No, you are very quiet, Daniel.
Yeah, from the
I think it's coming from that laptop.
Yeah.
Oh.
Could you tell something?
How about now?
No.
That better?
Yeah, from that? Oh, okay.
You're very fine, Daniel.
Okay, I've got my mic, I disconnected audio and reconnected audio and cranked my mic, so I don't know what happened.
It's like he has the wrong microphone. Maybe he's on his, no longer on his Bluetooth, he's on his.
So I was always on a USB microphone.
That's better, much better.
Okay. I didn't change anything, so I don't know what happened.
Okay.
Well,
right, so
slide,
to your question about 415, real quick, since
yeah. So on slide 14, so you can go through that kexec and the grub gexec version. So do you wind up leaving a different path of PCR evidence for later on to say that actually you have relaunched, or is the whole point that you recover the measured boot up to from the cold boot time, so that the next time, do you understand the question? I'm wondering whether the evidence of the relaunch, and if the verifier has to know about that, or does it always look like a cold boot?
So the answer to that is that what will happen is PCRs 0 through 15 will remain as they are. When you do the dynamic launch, the CPU using locality 4 will reset the PCRs in 17 through 22. So your PCRs will start with value 0. If you want an event that signifies that you went through a relaunch, then you would need some information and would need to be passed for it to be captured. One of the things to think about, though, is the whole purpose of doing the relaunch is you've reestablished what the root of your trust is, and you're rebuilding your trust chain. So only the stuff that's in control now is already in your trust chain. The question is what do you want to know about your previous trusted state that's no longer in control when you're in your new trusted state? If you just want to know that you did it, you can easily do some. We could easily make the the ability to measure some information. You can, that's one of the niceties of the SLRT is that you can base, since it's a TLV, you can stuff anything in it. And one of the things that we're doing with it is we're going to be able to do a dynamic policy that the DL stub will be able to walk through and measure what's been asked to get measured. That's one of the reasons why the patch series is there's a bit of rework to be done in the SL stub side of things. But that brings the benefit that you can pack extra information you want into the SLRT and just ask the SL stub to measure it to record that event for you.
The SL is on the right of that trust line, right?
Well, the SLT is the configuration information being passed from the previous trusted domain to the new trusted domain. Yes.
But the SL stub is on the right-hand side, so it's after the relaunch is what I'm saying. It's the new code. Yeah.
Yeah. The new code will be measured by the kernel or by the CPU, and then it can look at the SLRT, measure it before it acts on any information on it. So that way, there's been concerns about passing information over, and that's fine as long as you do the required measure before use. There's a couple of areas where we already have some issues that, just because of the nature of Linux, there's certain things that we just can't get measured before use, just a couple of command line parameters. And there's comments flagging that out. So it's things that we're aware of, and we try to make everybody aware of, but yes. To the backport question real quick. What I was trying to say is kind of putting the cart before the horse. I'd like to get stuff into the kernel before we start worrying about backporting it. But as far as older versions of the kernel, we've been developing on this series for some time. We have versions against the older kernels. It would backporting. There's documentation and evidence for anybody that would like to try to handle a backport. And if you if you want to have discussions about that, about what it would take to get that done, feel free to reach out to me. My contact info is I didn't put it on the slide. I apologize, but it should be on the LPC site, or just ping me on wire or on not wire. Sorry, on chat.
Hi, this is Art.
Hey.
I have a quick question about you mentioned resetting PCRs in locality 4 for this secure relaunch.
Mm-hmm.
This is like a hardware assisted feature, right? This is a side effect of the CPU instruction that you issue to pivot into the new context, or not?
Correct.
So on ARM, if you want to emulate this, basically we have a problem if we don't have special instructions to do any of this.
Yeah, so I don't know if you're familiar with the DRTM specification. Stuart,
Yeah, I was involved in the beginning, but I haven't looked at recent versions of it.
Okay. Yeah, so it is being done through an SMC call, and the design is to allow both software or firmware-based or hardware-based solutions. Obviously, the trust model on ARM is still built around. Forgive me. It's what's the levels? L0, whatever the firmware level 0 is. Yeah. So the roots for firmware-based, your root is based off of that. That's where your root of trust for all that's going to lie. So the benefit of this will come when there are hardware manufacturers that are ARM chip manufacturers that decide to adopt a hardware in the supported version. And it still will go through an SMC call, but the SMC call will be getting proxied to the hardware to trigger the event, and the hardware will have control of the TPM to do the locality enforcement. At least that's what my understanding of the intent is.
Yes, yeah. Okay.
Any other questions? Do we have any questions on chat?
I don't see any.
Nope.
Okay. Well, thank you, everybody.
Okay, thank you, Daniel, for joining us. I think that we have to wrap up our session. Sorry for the problems at the beginning with the audio, and I hope that we will see each other next year. Michał, want to add something at the end?
Yeah, I have announced the Birds of Feather session for the presentation about Linux Reset. Apparently, the location of this presentation has changed from the meeting room 6 to the hack room 5. So try to find the new room if you want to attend this presentation of Ron and Jonathan. Thank you.
The physical room is not changed. It's just add a virtual room.
So the name will be changed.
Yeah. So for this afternoon's Bird of Feather, the physical room doesn't change. It's hack room 5, hack room 6 upstairs, meeting room 6 upstairs. And if you are remote participants, so you can remote join through the hack room 5.
Okay, thank you for clarification. Okay, see each other next year. Bye, guys. Thank you for joining.